section 1.2, we had looked at different types of equations of two variables, and one of those types of equations that we had looked at were linear equations. So a linear equation is just an equation of the form y equals mx plus b, where m and b are some real numbers. So as an example, maybe something like y equals 2x plus 5. They don't have to be integers though. You could also have y equals negative 1/2 x minus 12, or maybe something even like y equals 0x plus pi. Right, this works because 0 and pi are real numbers. Of course, a better way to write this would probably be y equals pi. 0 times x is just 0. Right, but it has a y and an x in it, and notice that on the right-hand side, the exponent on your x term is just x to the 1. Alright, so notice that the right-hand side is really just a polynomial, so RHS means right-hand side, is a polynomial of degree 1. That is, 1 is being raised, or x is being raised to the first power. There's no x squareds or x cubed or anything bigger than that. I guess it could technically be degree 0 if your m value is equal to 0, like we had here. Okay, so let's look at how we would graph a linear equation. The simplest way is, if you're already given the equation of the graph, to just find 2 points on the line, graph those 2 points, and then draw a line through it. So the graph of a linear equation is going to depend on just 2 points on that line. So let's say we wanted to graph the equation y equals 3x minus 5. All I have to do is find 2 points on this line, and that would be enough to graph it. Now, we had talked about ways of finding points on a line in the last video. Let's say we wanted to find a point that has the form 0 comma something. This would be the y-intercept. All we have to do here is plug in x equals 0 and solve for y. So we'd have y is equal to 3 times 0 minus 5, which is just 0 minus 5, which is negative 5. So this would be the point 0, negative 5. Let's find another point on the line. When x is equal to 1, we would have y is equal to 3 times 1 minus 5, or 3 minus 5, which is negative 2. So we also have the point 1, negative 2 on this line. That's all we need. All we need is 2 points on the line to graph it. We have those 2 points, so I can now graph this equation by plotting the point at 0, negative 5. Oops. 4, 5, and then plotting the point at 1, negative 2, which is right here, and that's enough to sketch this whole line. Just draw your line through those 2 points. Try to draw it better than I did. I'm not very good at drawing. Alright, let's do another example. Say we wanted to graph this equation, y minus 4 is equal to 2 times parentheses x minus 1. This doesn't look exactly like that y equals mx plus b form that we had on the last page, but we could rewrite it that way if we wanted to. All we'd have to do is distribute the 2 on the right-hand side, and then move that negative 4 on the left over to the right. We don't even really need to do that, though, if we're trying to graph this, because we're just trying to find 2 points on the line, and we can do that even without rewriting this in y equals mx plus b form. Right, so to do this, pick an x value. Let's say we want to find first the y-intercept, so plug in x equals 0. We get y minus 4 equals 2 times 0 minus 1. That is, y minus 4 is equal to 2 times negative 1. It's negative 2. And adding 4 to both sides, I'd get y is equal to negative 2 plus 4, which is just positive 2. Okay, so my first point on this line is going to be the point 0, comma 2. Let's repeat that process again with another x value. We'll try the x value of 1, just like I did in the last example. So replace x with 1 in this equation. You'll get y minus 4 is equal to 2 times 1 minus 1. Well, 1 minus 1 is just 0, and 2 times 0 is 0, so the right-hand side is just 0. And moving that 4 over to the other side is going to give me y equals 4. Okay, so my other point is going to be the point 1, comma 4. Now that I have 2 points, that's enough to determine the graph of this line. So all we have to do is graph it. Okay, so I'm going to plot my point at 0, comma 2. That's a y-intercept of 2. Make sure you label your axes, and then plot a point at 1, comma 4. That's up here, and just draw your line through those 2 points. Alright, let's do just a couple more examples of graphing using points. These equations look a little bit funnier though. So we have equation of the form y equals 3. What's your x value here? How could you find 2 points on this line if you don't have any x values? Well, this equation is basically saying that your y value is always 3. It doesn't matter what your x coordinate is because the y coordinate of every point on this graph is fixed at y equals 3. So it's actually really easy to find points on this line. Just pick any x value you want. The y value is always 3. 0, 3, 1, 3, 12, 3, whatever you want, the y value is always 3. So what is this graph going to look like? Well, let's plot those points to find out. We've got a point at 0, 3. That's a y-intercept. We've got a point at 1, 3. This graph is just a horizontal line. Okay, well now we know what horizontal lines look like as an equation. It's just going to be y equals and then whatever the y-intercept is. Similarly, in an equation of the form x equals -2, the x-coordinate is fixed. You can't choose 2 different x values here and figure out what the y would be because the x-coordinate is constant, it's fixed. The x-coordinate is fixed at x equals -2. But the y-coordinate can be anything. Which means we can have points like -2, 0 or -2, 1. Because the x-coordinate is fixed at -2 and the y-coordinate can be anything. So let's graph this. We've got points at, whoops, I accidentally erased them. But our points were at -2, anything. -2, 0, -2, 1, whatever you want as long as the x-coordinate is -2. So those 2 points are here. That's enough to determine my graph, and we get a vertical line. So vertical lines are always going to be of the form x equals some real number, where that number is the x-intercept. And horizontal lines are always going to be of the form y equals a real number, where that number is the y-intercept. Alright, let's review some more information about linear equations, in particular the slope of a line. So we'll see when we talk about functions that slope represents the rate of change. But for our purposes, when we're just looking at the graph, the slope of the line is going to represent the steepness of the graph. So if your slope is a large number, that means that your graph is a very steep line. And if it's a small number close to 0, that means you have a very shallow line. So the way that we find the slope of the line is to find the rate of change, the change in y divided by the change in x. Change in y divided by the change in x. And so if your equation has a graph and it has points x1, y1, and x2, y2 as points on that line, then the slope is going to be the change in the y values. So that would be y2 minus y1 divided by the change in x values. It's x2 minus x1. Okay, that's how we find the slope of this line. Sometimes you'll hear it described as rise over run, because remember, the rise is really describing how much we're changing up or down. That is the change in the y direction. And the run is describing how much you're changing from left to right. That is, how much are you changing in the x direction. Okay, so let's look at a couple of examples of using this equation. So let's say that we have a line connecting, in the first case, the points -3, 4 and 2, -6. We're just going to use the slope formula to figure out the slope of this line. Alright, so in the first case, we're going to call these coordinates x1, y1, x2, y2. It doesn't really matter which one you label as each, as long as the x1 and the y1 go together and the x2 and the y2 go together. So according to our slope formula, the slope of this line, and we usually use the letter m to represent slope for whatever reason, is going to be given by the equation y2 minus y1 over x2 minus x1. Plugging that in, we get -6 minus 4. Right, that's y2 minus y1 over x2 minus x1. 2 minus -3. right? This is pretty simple to compute as long as you're really careful with your negative signs. On top, both of our terms are negative, -6 minus 4, so we get a -10. And on the bottom, we have 2 minus a -3. Whenever you subtract a negative, that's like adding a positive. So that's 2 plus 3 at the bottom. So our slope is -10 over 5, and 10 divided by 5 is just 2. So this slope is going to be -2. Okay, so what does it mean to have negative slope? We said that slope describes the steepness of a line. Well, if we were to actually graph this, if we were going to plot these points and graph it, we have a point roughly, I'm not going to draw this to scale, but at -3, 4 is somewhere up here, and at 2, -6 is somewhere down here. So this is what this graph of this equation roughly looks like. So notice that when the slope is negative, your graph is going to be going downhill from left to right. Right, your rate of change is decreasing. Well, your rate of change is negative, so it's going downhill from left to right. All right, let's do another example here. So we're going to find the slope of the line connecting the points 1, 3 and 2, 3. So here's your x1, y1, x2, y2. So according to our slope formula, the slope should be y2 minus y1 over x2 minus x1. That's going to be 3 minus 3 over 2 minus 1. That's 0 over 1. 0 divided by any non-zero number is just equal to 0. So we have a slope of 0 here. What does a graph look like when you have a slope of 0? Well, let's draw a picture and see. The points 1, 3, and 2, 3 are, let's see, 1, 3 would be about here, 2, 3 would be about here. Okay, so this looks like a horizontal line. In particular, the equation of this line is just going to be y equals 3. Because remember, we said for a horizontal line, the y value is fixed. So the y value is always 3. This is going to be the equation y equals 3. So when you have a horizontal line, the slope is 0, which makes sense, right? Because slope represents the steepness of a line. If this is flat, right, this isn't a hill, right, a mountain, it's not going uphill or downhill, it's just flat. So the steepness of that line is 0. It has no steepness. All right, what about this last example here? So we've got 5, 1 and 5, 2. Label them as x1, y1, x2, y2. Using my slope formula, I have y2 minus y1 over x2 minus x1. That is 2 minus 1 over 5 minus 5. That's going to give me 1 over 0. Uh-oh. You should be seeing red flags here. I'll draw one if you don't see it. This is a red flag. This is bad news. You can never have 0 in the denominator. 0 in the denominator is undefined. You can't divide by 0 because it doesn't make sense to divide by 0. You can't take some one number of objects and divide it into 0 groups. It just doesn't make sense. So this is undefined. And if we were to graph it, we would see that this is a graph that's a vertical line. Running out of space here. Right, but 5, 1 and 5, 2 are going to give me points at 5, 1 and 5, 2. And when I draw the line through those points, I get a vertical line. So just as a quick takeaway here, vertical lines have equations of the form x equals some real number, and they have an undefined slope. As opposed to horizontal lines, whose equations are always going to look like y equals some real number, and who have a slope of 0. Okay, these are just some important things to remember about lines. Alright, just a couple more definitions here. The slope-intercept form of a linear equation is one that we saw at the very beginning, at the very first slide. It's of the form y equals mx plus b, where m represents the slope, and b is always going to represent the y-intercept. Okay, this can be helpful because if we're given an equation of a form like this, y equals 1/3 x plus 4, of course you could graph this using the method we talked about before, finding 2 points on the line, But if we just plugged in 0 or 1, some of these numbers could get really messy depending on what your slope and y-intercept is. What we can learn from slope-intercept form of an equation is how to graph this without finding 2 points on the line directly. So here's what we do. We know that the slope is the number that's attached to the x, right? The coefficient on the x term. So the slope of this equation is going to be 1/3. And the y-intercept, that's going to be the constant term that's off on its own. So the y-intercept of this graph is going to be equal to 4. Knowing those two things is enough to graph this without finding any other points on the line directly. Right? You start with the y-intercept of 4. I know that this line is going to cross the y-axis at 4. Okay? Now I also know that the slope is 1/3. So how does that help me to draw this graph? Well, remember that 1/3 means that we have a rise of 1, positive 1, and a run of positive 3. So starting with any point on the line, we had a point here at 4. You can find the next point on the line, or another point on the line, by rising 1, that means go up 1, and then running 3, go over 3. So starting at this y-intercept, I'm going to go up 1, then over 3 units. That's going to bring me here to a point at 3, 5. And using these 2 points, we can now just graph our line. Alright, since they were both positive, we were rising up and running to the right. If one of those had been negative, then you would have had to either go down or run to the left instead, and that would have given you that negative slope that you're looking for. Alright, so this can just be a quicker way of graphing a line. Now, it's often useful to use a different form of an equation called point-slope form. So point-slope form of an equation looks a little bit messier. Y minus y1 equals m times x minus x1, where m is going to be a real number that's going to be, I shouldn't use equal here, m is going to be the slope of the line, or the slope of the equation. And these other two values, x1 and y1, these are going to be real numbers, and they're going to represent a point on the line. So x1 and y1 is a point on the line. I shouldn't say are. This is a point on the line. Alright, so if you see an equation that looks like this, y minus 2 equals negative 2/3 times x plus 5, this is an equation that's written in point-slope form. So we can pull out the important information here, namely the slope, that's going to be your negative 2/3, and then a point on the line, that's going to be determined by those constant terms, and that'll tell you a way to graph this equation without actually finding points using our original method. Okay, so we know that the slope is negative 2/3. What would the point on the line be? Well, it looks like we should just be able to pull out the x1 term from inside the parentheses and the y1 term from over here. The problem is, what we want to be careful of is that in point-slope form of an equation, it's always going to look like y minus the y1 term. Okay, that makes sense here. That matches what we have in this equation. But on the right-hand side, it should be x minus the x1 term, and we have x plus the x1 term. So how do we fix this? Well, what we can do is go ahead and rewrite this equation. Leave that y minus 2 alone because that looks how we want it to look, as y minus a constant. We have negative 2/3 on the outside, and I'm going to rewrite the inside as x minus negative 5, just so that it matches the point-slope form that you see up here. Alright, now that it's written in this same format, now I can actually pull out that x1 term and the y1 term to get a point on the line at negative 5, 2. Okay, this is enough to graph this equation. Just plot your point at negative 5, 2, negative 5, 2, and then use the slope to get the next point on the line. So our slope, we had said, was negative 2/3. That means we're going to rise negative 2, meaning we're going to go down 2 points, and then we're going to run 3. We'll go to the right 3 points. So go down 2, and then 3 to the right. You can continue to find the next one if you wanted to by going down 2, and then 3 to the right. Right, and once you have 2 points on this line, I didn't really have to do 3, but once you have 2, you can draw your line and graph it that way. All right, let's do one more example of this. What if we wanted to write the equation of a line passing through the point 2, 4, and 6, negative 1? I probably should fix this here. There's infinitely many correct ways to write the equation of a line, so I just want one possible way of writing the equation of a line. But if you're given 2 points on the line, your first step should always be the same, and that should be to find the slope. All right, we've already done a bunch of examples of that. We need to use the slope formula, y2 minus y1 over x2 minus x1. All right, so that's going to be, if I label my points here as x1, y1, x2, y2, then my slope is going to be given by negative 1 minus 4 divided by 6 minus 2. That is negative 5 over 6 minus 2 is 4. All right, so I have slope. Now, if you wanted to write your equation in slope-intercept form, you could, but you would still have to solve for the y-intercept. That's work, right? That's extra work. This is why it's useful to know point-slope form, because we already have a point on the line. In fact, we have 2 of them. But as long as you have at least 1 point and you have the slope, that's enough to write the equation in point-slope form. That looks like y minus y1 equals m times x minus x1. So I can just plug this right in and get the equation y minus my y1 term, which was 4, equals m, the slope, that's negative 5 over 4, times x minus the x1 form. That's 2. There's nothing special about 2, 4. I also could have written the same equation using my other point that I knew was on the line, 6, negative 1. That would look like y minus negative 1 equals negative 5/4 times x minus 6. This is an equally correct equation of this line. Right, either one of these works. And there's infinitely many more because you can take any point on the line and plug it in. As long as that point's on the line, it will give you a correct equation. All right, our last couple definitions have to do with special types of lines, namely parallel lines and perpendicular lines. So parallel lines is just a name that we give for 2 linear equations whose graphs never intersect. So as an example, something like this and this. Right, they're like railroad tracks. They're going the exact same direction. They never intersect. They have the property that they're always going to have the same slope. In fact, 2 lines are parallel if and only if those lines have the same slope. Now we contrast those often with what we call perpendicular lines. Those are lines that intersect at a right angle or a 90-degree angle. I didn't have a degree symbol there. Okay, and perpendicular lines are going to have opposite reciprocal slopes of each other. So for instance, actually, the x and the y-axes are examples of perpendicular lines, right? But they don't have to be vertical and horizontal. You could have perpendicular lines that look something like this. As long as they meet at a right angle, they're going to be perpendicular lines. And the neat thing is that they have opposite reciprocal slopes of each other. So let's say this blue line has a slope of, it looks like maybe, I don't know, about 1/3. Then I know that that green line, if it's a perpendicular line, is going to have the opposite reciprocal slope. Opposite means the sign will change. The blue line has positive slope, so the green line has negative slope. Reciprocal means flip the fraction around. So if I flip the fraction of 1/3, I'm going to get 3 over 1. So the green line would have to have a slope of negative 3 over 1, or you could rewrite that as just plain negative 3. Okay, so perpendicular lines always have opposite reciprocal slopes of each other. One last example. Given the graph of the equation y equals 2/3 x minus 5, right, this is an equation in slope-intercept form. We're going to find the equation of a parallel line passing through 4, 2, and the equation of a perpendicular line passing through negative 1, 3. All right, so 2 things that we're going to pick out of this original equation here, which we may or may not find useful, but they're there, so we may as well write it down. Our slope, right, this is our m. This is of the form y equals mx plus b. So our slope is the m. Your slope is going to be 2/3. And the b term is your y-intercept. The y-intercept is -5. Now we want to write the equation of a graph that's parallel to this line, passing through the point 4, 2. Parallel means it's going to have the same slope as the original equation. So my new equation is going to have a slope of 2/3 because the original one had a slope of 2/3. We also know that it's going to pass through the point 4, 2. So now we know the slope of the line and a point on the line, which means I can use point-slope form, y minus y1 equals m times x minus x1, to write the equation of this line. Right, remember, 4 is going to be your x1 and 2 is going to be your y1. So plugging this all in, we get the equation y minus 2 equals 2/3 times x minus 4. That's your equation of your parallel line. Next, we want to find the equation of a perpendicular line passing through the point -1, 3. Alright, well, if it's a perpendicular line, it's not going to have the same slope that the original equation had. It's going to have the opposite reciprocal slope of 2/3. What's the opposite reciprocal of 2/3? Well, the opposite sign would be negative, because this original one was positive, and the reciprocal of 2/3 would be 3/2. So my new equation is going to have a slope of -3/2. And again, they've given us the point -1, 3. So that's your x1 and your y1. So again, it makes sense here to use point-slope form because we have the slope of the line and a point on the line. That's y minus y1 equals m times x minus x1. If you're sick of copying this down, just memorize it and then you won't have to copy it down every time. Alright, the slope of this is -3/2 and our point is at -1, 3. So plugging everything in, we get the equation y minus 3 equals -3/2 times x minus -1. And if you like, you could replace that as x plus +1. So there's the equation of our perpendicular line.